Now, once you think you understand simplifying the square root of a variable expression, you often get tripped up by a different example than one either your teacher taught or that you are practicing on your homework by yourself. So in this video, what I want to do is go over 10 more examples that we can work through together step by step to make sure that we really understand what we're trying to accomplish on simplifying square root expressions. Now, if you're struggling still a little bit, then please go ahead and follow along with me. And if you think you have a great idea already of how to do them, then feel free to work ahead and use this video to check your work as well as your answers at the end. All right, let's go ahead and get started. All right, so remember the whole goal of simplifying a squared expression is rewriting our terms as something squared, because we can always take the square root of something being raised to the second power. So in this case, what I want to do is find the largest squared number that evenly divides into 72, because 72 is not a square number. Okay, and now you can see that out of all of these numbers, because I can't go up any higher to divide into 72, that 36 is the highest number that divides into 72. And again, that divides into it evenly. And 36 is a square number because I can rewrite that as a 6 squared. So all I'm simply going to do is rewrite 72 as a 36 times 2. Now I can break this up into a square root of 36 times the square root of 2. Square root of 36 is going to be 6 times the square root of 2. Now, in this next example, hopefully you recognize that 64 is indeed a square number. So I can simply go ahead and take the square root of that, or I can rewrite that as a 8 squared. What I'm also recognize here is a cubed is not a square number. However, using the power rule of exponents, I can rewrite that as an a squared times a. So if I just break everything up in terms of squared numbers, it can look something like this. Now, this is the exact same expression. It's just written as terms raised to the second power. And the reason why I want to do that is because now I can break up my terms. Now, don't worry about the 5 on the outside because that's just a number that's being multiplied by a radical. We can still break up the radical for each of these terms because they're separated by multiplication. So now you can see I can just simply take the square root of 8 squared as well as the square root of a squared, which is just going to leave me with a 5 times 8 times an a times the square root of a, which is going to give me a 40a square root of a. Now it's important also to understand that since I'm taking the even root and my ending outside of my radical has an odd power, I can also put absolute value just to make sure that we understand that that is indeed going to represent a positive value. All right, in the second example, I have the square root of 121 times x to the 4th times y to the 16th. Now, one thing I notice here is 121, that is a square number. So I can rewrite that as 11 squared. Now my x to the 4th and y to the 16th, I could use the product rule here for x to the 4th, right? I could write this as x squared times x squared, but to the y to the 16th, I don't want to write y squared that many times. So what I'm going to do is I'm going to rewrite that using the power rule. So when I do that, it's going to look just like this. Now again, notice how I wrote this as a y to the 8th squared instead of a y squared to the 8th, because remember, I can only take the square root of something being squared. And again, I decided to write the x to the 4th as a power rule as well. Now I could break these up one by one, but I think now that you've seen my other two examples, you realize that I can take the square root of these just kind of separately without writing them. So therefore, I'll be left with a 11x squared y to the 8th. Now in example 4, now I have 3 variables. There's many different ways you can do this. Again, you can use the product rule or you can use the power rule, but now I'm also going to show you how to use a mix between the two. So rewriting this as terms that are going to be raised to the second power, I could rewrite this expression just like this. Okay, so now what you can see here is I rewrite 40 times 4 times 10. I rewrote a cubed as a squared times a, rewrote b to the 4th as a b squared squared, and I rewrote c to the 5th as a c squared raised to the second power, which is technically c to the 4th, and then multiplied times an extra c. Now, another way we can do this is we can also break up our radical rather than breaking it up for each and every term, which sometimes when you're doing a large problem can be a lot of work. We can also now separate this to terms we can take the square root of to terms we cannot take the square root of. So if I'm going to do it this way, the way I can do that is just looks like this. So basically what I did is I just took all the terms that were squared. So I could write 4, a squared, b squared, and c squared, and I put them under this radical. And again, I'm multiplying them by whatever's left over, which is a 10, a, as well as a c. Now here, I can't simplify this any further, but since these are all square terms, I can now just simply take the square root of them. So my final answer is going to be a 2a, b squared, c squared times the square root of 10ac. All right, now question number 5, you can see we have 4 variables. So again, it just kind of gets into this habit of how do you want to break up your radicals? Do you want to break them up using the product rule, the power rule, or a kind of a mix of both? So in this example, that's exactly what I'm going to do. I'm just going to break it up just like this. So you can see again, all I'm doing is using the power and the product rule to get to my same powers. If you multiply each of your terms, you're going to get back the original expression. But again, what's so important about this is now I can identify the terms that I can take the square root of and those that I cannot. And now just to simplify them, you're just going to basically undo the square root and the squaring term, leaving me with a final answer of a cubed b to the 9th d squared times the square root of a d. Now it's important to recognize here that I have a to the cubed and b to the 9th. Those are both odd. So since I took the square root and I have an odd value, we want to make sure that we're only talking about the positive version of this. So therefore, again, I'm going to use an absolute value. Now we don't need to do this for the d squared, because even if d was a negative number, since it's being squared, that's always going to return it to be a positive value. But for the 3 and to the 9, if it was negative, then that would give us a negative number, which therefore we would not be able to take the square root of. Now, so a lot of people remember you can't take the square root of a negative number. That's why using the absolute values is important to be detailed. Now, in this example, though, people see the negative under the radical and they say, I can't take the square root of a negative number. But it's very important to understand what exactly you're doing. This negative 3x, yes, it is under the radical, but it's being raised to the 10th power. So therefore, you're going to have to take the square root of this 10th power before you get inside of this parentheses. So technically, you're not really taking the square root of a negative number. This negative 3x is being raised to the 10th power, then you're taking the square root of that. And it's important to know that anything negative raised to an even power will indeed be positive. So all we simply need to do then is rewrite this. And again, I don't want to rewrite negative 3x times itself 10 times. So what I'm going to do in this example is rewrite it using the power rule. And again, it's so important, guys, to rewrite this as raised to the 5th power squared, because again, I can only take the square root of something squared. You can see those are inverse operations, leaving me with a final answer of a negative 3x raised to the 5th power, which again, we know has to be positive, ladies and gentlemen, right? Because you can't take the square root of a negative number. Therefore, we're going to use the absolute value. All right, and question number 7, it's very similar to the previous example. And we see the negative though is on the outside. So remember, that's just a scalar. It's just multiplying by your expression. Another thing that people see though, is they see this expression. They want to distribute the a squared or the square root to the a squared and the 4a because they see those as square numbers, but please do not do that. Again, this expression is being raised to the 12th power. So we're going to have to just simplify that. But even if that 12 was there, we cannot distribute the square root across addition and subtraction anyways. Make sure you don't do that. That's a very common mistake that students will make. So in this example, I'm just going to rewrite this expression using the power rule raised to the 2nd power. And now you can see I can take the square root of that squared. That's going to leave me with the final answer of a negative a squared plus 4a raised to the 6th power. And again, since it's even, we don't need to include this absolute value because this negative here is just multiplying the final answer. Now, question number 8, again, we're just looking for what is a square number that evenly divides into that. Again, we can break this up into 100 times 2, and then I can rewrite this using the power and the product rule. And now I can just go ahead and take the square root of all of my square terms, which is going to be 100, an a cubed raised to the 2nd power, and a b cubed raised to the 2nd power. So I'll rewrite those under their own radical, and all the ones that I cannot simplify in the other radical. Now I can just take the square root of each and every one of these terms. And again, you could break them up separately if you want to, but we can just leave it as a 10 a cubed b cubed times the square root of 2b. So in these two examples, students usually get mixed up because they see the fractions. But I don't want you to overthink when we have fractions under radical, because just like we can separate our radicand across multiplication, we can also separate it across division. So I can rewrite this problem just like this. So now I've separated by multiplication. Now let's go and separate this by our division. Okay, so now it's time to go ahead and simplify. And you can see here the square root of 8, I can rewrite that as a 4 times 2. So I'm just going to go ahead and break everything up. So 4 times 2. I can rewrite that as a square root of 3 squared because that is a square number. Now for my variables, I'm just going to break these up using the power and the product rule. And again, I want to make sure that I'm having them raised to that 2nd power. Anything left over, I'll use the product rule. So you can see here, I broke up 8 as 4 times 2 and 9 as 3 squared. For x to the 7th, I did a 3 raised to the 2nd power, which is x to the 6th times x. For y to the 20th, I did y to the 10th raised to the 2nd power, which is y to the 20th. And then z, I did the same thing, but I had to multiply by an extra z to get my z to the 21st power. Now let's just go ahead and simplify and take the square root of everything that we can take the square root of. So I can take the square root of 4, so that's going to leave me with a 4. Square root of 2. Square root of 3 squared is just going to give me a 3. And then I'm going to, let's see, what can we pull out? Well, I can take the square root of x cubed squared, so that's going to be times an x cubed. Then I have a y to the 10th, take the square root of that, and then I have a z to the 10th. And then what's left under my square root is going to be a x times a z. Now I can just simplify this one more time. I can multiply these two radicals. Just like how we separated them, we can now bring them back together, and I can write this as a fraction. So that's going to give me a 2/3 x cubed y to the 10th z to the 10th times the square root of a 2xz. In this last example, I have a 1/2 times the square root of 1 over 81 times a to the 5th times c to the 8th. Now, you could just break up the radical like we did over here, but hopefully you recognize if I was to take the square root of 1, that's just 1, and the square root of 81 is 9. So hopefully you recognize that I can just rewrite this as a square root of 1/9 squared, right? Because 1/9 times 1/9 is going to be 1 over 81. And then I'll just rewrite my a to the 4th and c to the 8th using the power and the product rule. Okay, so now I can just take the square root of each of these terms squared. Again, the 1/2 is just my scalar multiple, so I'll just leave that on the outside. So therefore, I'll have a final answer here of a 1/2 times a 1/9 times a squared times a c to the 4th all over the square root of a. And then I can just simplify this a little bit more, and I'll just rewrite this as a 1 over 18th a squared c to the 4th times the square root of a. There you go, ladies and gentlemen. That was 10 examples of simplifying the square root of a variable expression. I hope this was helpful, but if you need more examples or you want to see a bigger variety, check out the examples that I have for you down below, or go ahead and check out my next video that I have for you right here.